Okay, let's dive right into this explainer. Today, we're going to completely demystify the magic of heap sort, and we're doing that by focusing on our core topic, exactly how memory shifts behind the scenes during the heapify steps. We're going to strip away all those high-level abstractions and look at the raw physical mechanics of sorting in place. So here's a question to get us started. How exactly do you fit a branching 2D tree into a completely flat line of memory? This is really the heart of our journey today. Because you know those beautiful, symmetrical tree structures you picture in your head? Yeah, they're an illusion. The physical reality of your computer's hardware is just a continuous, flat line of data. Think of it like a long row of houses on a single street. You literally cannot stack them into a branching tree physically. They just sit there, side by side, sequentially in RAM. Here's our roadmap for this explainer. We're going to start by breaking down that binary tree illusion. Then we'll see how to build a max heap, hyper-focus on those core heapify memory steps, check out the time and space complexity, and finally, we'll hit the memory cache problem. Right, so let's jump straight into part one, shattering that binary tree illusion. Whenever we talk about heap sort, we instinctively draw these elegant branching trees. It makes perfect sense for our mental whiteboard. But to the computer, it just sees a rigid one-dimensional array. Everything, the whole sorting process, happens right there in that flat line. It's what we call an implicit data structure, and that's really just a fancy way of saying it takes up absolutely zero extra space beyond the array of items you're already sorting. There are no actual node objects, no physical pointers holding this tree together in memory. It's all just an illusion. Well, if there are no pointers, how on earth do we move around? This is where the magic index math comes in. These simple formulas act as invisible wires connecting our flat array, letting us navigate it as if it were a tree. If you're looking at a zero-based array, your root sits comfortably at index 0. Want the left child of any node I? Just calculate 2 times I plus 1. Right child? 2 times I plus 2. Let's make that concrete. If you're at index 2, your left child is magically waiting for you down at index 5. This basic arithmetic is the secret sauce. It maps our mental model directly onto continuous memory without wasting a single byte on pointers. Okay, armed with our mathematical map, let's move right into step 2, actually building the max heap. So before we can sort anything, we have to take our initial chaotic data and reorganize it to satisfy the heap property. This takes some really clever logic, essentially building small heaps and repeatedly merging them. Imagine starting right from the middle of the array, which is essentially where the last non-leaf nodes live, and working your way backward to the start. As we go, we use a pull-down or sift-down operation on each node. We're physically shifting the elements in memory to make sure each little subtree forms a structurally sound max heap. And what exactly is that rule we're enforcing? It's the max heap property. Every parent node absolutely must be greater than or equal to both of its children. So by iterating backward over that first half of the array and relentlessly applying this rule, the largest elements naturally bubble up through the branches. The entire goal here is singular. Once we're done, the absolute maximum value in the whole array is going to sit proudly right at index 0, ready to be extracted. Now that our heap is built, let's dive into our absolute main focus for today, the core heapify steps. This is where the real action happens. During the sorting phase, we grab that largest value at the root and swap it to the end of the array. But in doing that, we deliberately break the heap structure. We're left with a damaged binary heap, usually with a tiny, awkward value sitting way up at the top root position. To fix it, we run through a micro-narrative of 4 precise memory steps. First, we compare this newly demoted root with its left and right children. Second, we find the absolute largest among those 3. Why? Because the heaviest weight needs to rise to support the branches below it. Third, if one of the children is larger, we physically swap them in the array. And fourth, we recursively trigger this process, heapifying down the newly affected subtree as our displaced root continues its downward journey. Tracing this visually is just fascinating. As this sift-down process runs, you can literally watch the elements cascade through the subheaps, level by level. When a root is smaller than its greatest child, they exchange physical places in that flat array using exactly those mathematical indices we talked about earlier. The demoted root gets pushed down a tier. And this repeats, right? Filtering the element down, checking, swapping, until it finally hits its valid mathematical resting spot where it is strictly larger than anything below it. And you have to remember, this entire elegant cascade is happening directly within the contiguous memory blocks of the array itself. No extra lists, no extra trees. We extract the max, shrink our considered heap size by 1 at the back, and call sift down to repair the front. We do this n times. As we keep promoting the greatest remaining child to the root and swapping it to the back, we are literally building a solid wall of perfectly sorted elements from right to left, while the chaotic, shrinking heap stays safely contained in the front.
Of course, all this careful sifting and swapping comes with specific performance metrics. Let's look at our fourth section, time and space complexity.
Because our heapify algorithm only ever travels straight down the height of the tree, which is logarithmic, it guarantees a highly favorable worst-case runtime. Actually building the initial heap is an O of n, linear operation. Then each extraction and subsequent sift down only takes O of log n time. Think about it. It never scans the whole array during the sort, it just walks down the tree's height. Doing that n times gives us a rock-solid, predictable worst case and average runtime of O of n log n. But here is the massive win for Heap Sort. It achieves this incredible efficiency completely in place. It requires absolutely zero additional memory overhead beyond the original array itself. That gives it an auxiliary space complexity of O of 1. And that makes it an absolute darling for embedded systems, avionics, or real-time computing. Places where memory limits are super strict and running out of RAM is simply not an option.
But wait, if Heap Sort is so mathematically perfect and memory lean, why isn't it the absolute fastest algorithm out there? That brings us to our final section, the memory cache problem. If you look at the theoretical trade-offs against a fierce rival like Quicksort, Heap Sort seems like the clear winner on the time and space rows. It boasts a better worst-case time and uses less overhead space. But the secret killer lies right there in that third row, memory access. Notice how Quicksort accesses memory sequentially, while Heap Sort is forced to jump around completely randomly. Here's why that matters. Modern CPUs load data in contiguous chunks called cache lines. So arrays provide excellent memory locality if you process them sequentially. It's kind of like reading a book page by page. It's fast and predictable. Quicksort naturally processes elements right next to each other. But in Heap Sort, our beautiful 2 times I plus 1 index math forces the CPU to jump wildly across the physical memory layout. Imagine being forced to jump to a random page for every single word you read in a book. Leaping way ahead in the array to find a child node causes frequent CPU cache misses, which forces the system to slowly fetch from main memory over and over again.
Ultimately, an algorithm is only ever as fast as the physical hardware allows it to be. This quote from the source material perfectly sums up the conflict between elegant math and harsh hardware realities. Despite its constant space and that perfect O of n log n theoretical time, the heap inherently requires random memory access to execute those core heapifying operations. And those constant jumps cause cache misses that severely drag down its real-world execution speed compared to something like Quicksort. So it mathematically guarantees O of n log n time with O of 1 space, but it's ultimately betrayed by the physical reality of modern CPU cache architecture. Which leaves us with a fascinating question. Is Heap Sort the greatest algorithm we rarely use? I'll leave you to ponder that beautiful irony. I really hope this deep dive into the core heapify memory steps has given you a profound new appreciation for exactly what happens under the hood when we sort.